Okay, so let's get started. So I would have liked to have covered this before the quiz so that we started on a new note today, but there's one small topic that is still left over. We were talking about least squares problems, and as I mentioned, least squares problems are among the most commonly encountered problems in engineering. And we looked at linear least squares problems. Today we will complete the loop and look at non-linear least squares problems. Okay, that's the first half of today's class. Okay, so in particular, the method that we're going to talk about today is a very traditionally well-known, well-used, and very popular method. It's called the Gauss-Newton method. Okay, many of you may have heard of this. And we are already familiar with the Newton method, right? The Newton method, we'll summarize it now, plus some kind of a a small set of modifications to deal with the fact that the objective function is written in least squares form. That's what the Gauss-Newton method is. Okay, so let's quickly recap. In fact, this was a question which you did yesterday, right? You want to recap the Newton method. What is the first thing that you want to do after picking the initial point? Even before that, I mean, you need to first calculate the gradient and Hessian, right? So let's just say that you need to first calculate, because it's not going to be given to you, right? So calculate grad f and the Hessian, okay? And after having calculated, you need to check if this is positive definite. Let's assume that for simplicity that it is positive definite, okay? Next, after having gotten these two quantities, what do I compute next? The Newton direction, right? So calculate the Newton direction, which is simply the solution to this, right? So del squared f into p is equal to minus grad f. Right? I need to solve for p in order to get the Newton direction, right? So solve for okay, what would be next? Calculate the step length. There are many strategies for this. Wolf conditions will help us with inexact line search. That's the most practical thing, because exact line search is almost always impractical. So let's say we did it. After we got our step length, what do? We do the update, right? So we will do xk plus 1 is xk plus alpha k pk. I move to the next step and I'm almost done. What do I need to check now? Check for convergence, right? So check for convergence. I'm leaving it general. This convergence could be you've exhausted your maximum number of iterations, or mod norm of grad f is very low, whatever, right? And so if so, stop, right? Else I go back to which step? Step 1, right? Else go to 1. This was our this is the general, this is a recap of the Newton method in general. Here we did not make any assumptions on the form of f. F can be any function. This is how we have studied the Newton method. Now let's specialize it to the extra information that is being given to you, that f is composed of a sum of squares, right? That's what a least squares problem is. So now let's make the specialization. So specialize that f we had written it in this form, right? A sum of residual squares. So this is in the least squares problem. And the advantage of writing it especially in this way is that you get some special form of the gradient Hessian, etc. Right? Everyone remembers this sum of squares? Each of those components of Rx is, for example, what? The difference between a measurement and a model. Right? The prediction of the model and the measurement, that's what I have in Rx. So, what was grad f? We had a nice form for grad f, remember, in terms of the Jacobian of R, right? So, I had J transpose x times Rx, right? This was my gradient. Similarly, I had a nice expression for the Hessian, right? So, I had a J transpose x Jx, that was the first term, and the second term was a summation. There was no nice closed form expression, so I just wrote it like this, right? So, this is my gradient, this is my Hessian, right? And the place where the Gauss-Newton method actually begins, this is just a recap of least squares problems, was an observation we had made previously. This term over here, we had said that there are some conditions under which this term can be low in magnitude, right? So, does anyone remember what those conditions were? Okay, one is if R is linear is not the exactly correct word, affine, affine. If Rj is affine, then by the time I take the Hessian of R, I am going to get 0, right? So, when can I ignore the red term, right? And the second was when I am actually reach close to the solution, when I reach close to the solution, the residual is going to be small, right? So, close to the solution. Okay. And then when in either of these two situations, it is reasonable to approximate the Hessian like this. Okay. Just by looking at this, is what is the advantage of having the Hessian in this form as opposed to the general form? Is there something that pops out? It looks to be positive. It seems that very easily it could be positive definite. Why? Because if I do Z transpose grad squared f Z. Okay, so we said that possibly one of the advantages of this is that this is easy for me to check whether it's positive definite or not, and the easy way to look at it is this expression. What does this become? Norm of Jx times Z squared. So, this is going to be, if I want it to be positive definite, that means I want this to be greater than 0, and this will happen under what condition? J has to be full column rank. J cannot be any matrix. J has to be full column rank. Then this expression will always be greater than 0 for non-zero Z. Remember, for positive definite, I have to consider all possible Z, but they have to be non-zero, right? So, implies that J must be full column rank, and this is a easy enough condition to check. Okay. So, all right. So, that is one of the advantages of this approximation, that advantages of the approximation. So, remember, before I go further, in our original Newton method, I had to check at each step if my Hessian was positive definite, and that can be in general, if I give you some function del squared f, it's not an easy thing to check, because if you didn't know anything, how would you check whether a matrix is positive definite? You would have to, for example, calculate the eigenvalues. That's an expensive operation. On the other hand, because I am specializing my problem as a least squares problem, A, B, what else? If I am in a position to ignore the second term of the Hessian, then all I have to do is check full column rank, which is not as expensive an operation as calculating eigenvalues, right? So, this is a substantial advantage that we get, okay. So now what we'll do is we'll just work out what is this Gauss-Newton method now. So in the Newton method, step 1 we have done, calculate grad f del squared f we have done. Next is calculate the Newton direction. So let's see, does this calculation become anything easier, right? So calculating the P Newton, right? So what was that? Del squared f into P is equal to minus grad f. So what is del squared f under the approximation? J transpose J, P remains here, and grad f was J transpose R. Okay, these are not all constant, so I mean just all are functions of x. Okay, they look like constants over here. Okay, actually we should be putting the subscript for the iteration on each of these. Okay, so we need to solve for pk. Okay, I get my once I get this, I calculate the step length. Calculating the step length moves me to the next point. Okay, and convergence is of course grad f, norm grad f is tending to 0. That's how the usual Newton method works. Okay, so in a nutshell, this is what the Gauss-Newton method does. It ignores the second part of the Hessian, and you are calculating the search direction each time by solving this system of equations. Okay, and you're doing search, inexact line search to get alpha, and that's, so it's very similar to the Newton method, except a few simplifications are coming because I just called it a least squares problem. Okay, so one thing, what was the, if you can recall, what was the reason that I wanted to check for positive definiteness of the Hessian? No, full column rank tells me that it's positive definite, but why do I want to check whether it's convex? So that the descent direction, so that the direction pk is actually a descent direction, right? So if you, let's just look at this once again, right? So P is a legit that means that pk transpose grad fk, this expression should be what? Positive, negative, 0, negative, right? Should be less than 0. Then it is a descent direction because I am going in the opposite side as grad f. So now if I just substitute what I know of grad f, so this is pk transpose, grad f was what? J transpose R. So this is J transpose RK. Okay. J transpose RK. I have this equation over here, which has an expression for J transpose RK exactly inside it, right? So I can substitute this in here. Is everyone with me on this? Right? So this would become pk transpose J transpose J pk. Okay, and there is a minus sign, right? The minus sign should have come, no, there's no minus sign here. Where is the minus sign? Where does the minus sign comes here? Yeah, okay, fine. This can be very conveniently written as norm squared of something, right? So this is norm squared of jk pk, right? And you can see this is definitely something that is less than 0. Okay. Now when is less than 0? When jk is full column rank. Okay. When will this go to 0? Will this go, if it is full column rank, when can this expression ever go to 0? When can this expression actually go to 0? One step before that. jk is full column rank, so obviously it cannot be 0. So what is the option? pk has to be 0. So only condition is pk going to 0, and pk going to 0 tells me what? You've reached. But how do I relate pk to, can I relate pk to anything else? Del f, right? So what is grad f? How do I relate pk to grad f? I can use this expression, right? Right. So if I substitute p equal to 0 into this top expression over here, so this is going to get me, so the Newton equation, the Newton condition, right? This is equal to minus grad f. So this will imply that grad f is equal to 0, and grad f equal to 0 is what? Is the condition of stationarity, right? So this is the stationary condition. So this is, I mean, we knew that it is going to be a legitimate descent direction. We see that it is a legitimate descent direction because J is full column rank. So when it actually goes to 0 is when my iterations have come to an end, because it can only go to 0 when my grad f is 0. Right? The final note that I want to make is now do one final connection between this non-linear least squares problem and the least squares, linear least squares problem. So what is the equation that we are solving at each step? This guy. This is the equation that I have to solve at each iteration in order to get pk, right? So supposing you wrote a piece of MATLAB code that solves a linear least squares problem, and you want to reuse that piece of code for the non-linear least squares problem. This is an example of how you would do it. So let's just look at this equation. So jk transpose jk times pk is equal to minus jk transpose rk. This is what we have to do, solving for pk. We can do a little bit of algebra over here. Can I take some term common from both? jk transpose can be pulled out, right? So this is the same as saying that jk transpose jk pk plus rk is equal to 0, right? Now you all are by now experts at taking gradients of various expressions. Does this expression look like the gradient of some well-known expression? This looks like A transpose Ax plus B, and that is the gradient of what expression? Norm of Ax plus B whole squared, right? So this is the same as, let's say this is equivalent to right. We arrive at this by taking, if I take this expression, take the grad, I get this expression. And this expression over here, doesn't it look like your, if you just scroll back in your notes, this looks exactly like your linear least squares problem, right? In the linear least squares problem, your A was your jk, and all of these terms are exactly like that, right? So I mean, this is, I don't even have to look at that. This is essentially something like Ax plus B whole square, which was what my linear least squares problem was anyway, right? So what is the conclusion over here? In your non-linear least squares problem, at each iteration you are solving one step of linear least squares problem. So if you had written that piece of code as a function, you could just call that at each step. What is the output of this solving the linear least squares problem? What do you get out of it? You get the direction pk. It gives you pk, right? The solution to this is p. You get your p. Once you get your p, if you have, by now you would have already written some pseudocode for inexact line search, that will give you your alpha, and you are in business because now you can go to xk plus 1. Okay. So if you have a, you know, your research problem which is non-linear least squares, and if the Hessian approximation is looking like, you know, you can make it, if it's a reasonable approximation to make, you can very easily get started with this. Okay. Any questions on this? Quite straightforward, right? It is almost, there's almost nothing new over here. It's just based on a slight modification of Newton's method, or rather taking Newton's method and pouring it into the least squares formulation. Overall, okay, so he didn't get how this is non-linear least squares. The point is, okay, let's look at here. So let's look at the Hessian. If this were linear least squares problem, your Hessian here would be constant. It would not be j as a function of x, would be constant. Here the trouble is that at each step your Jacobian is going to change, right? In the linear least squares problem, j became a fixed matrix, but now it's j as a function of x. That's the difference. That's why you have to do it iteratively. So all your tricks of what should I say, truncated SVD, this, that, and the other can be applied now to each of the iterations. Yeah, well, whether you replace call b prime equal to minus b, doesn't matter. The form is the same. It's ax plus b or ax minus y.